Hello there, my name is Anne. Thank you so much for joining me in today's video where I'm going to be talking about planar graphs and Euler's formula, mainly how they're connected and how we can use Euler's formula to verify planar graphs. If you find this video helpful, please don't forget to give it a like or share it with someone that you think might also find it helpful. Anyway, with all that said, let's get straight into it. Okay, you know the drill. We're going to start by understanding what a planar graph is. So a planar graph is one that can be embedded in a single plane. What that actually means is that it can be drawn in 2D without any edges crossing. On the screen here, you can see an example of a planar graph on the left, and you'll notice that the edges aren't intersecting with each other. Whereas with my non-planar graph example on the right here, the edges are intersecting at multiple points, which makes it non-planar. Now, the little caveat here is that graphs that initially appear to be non-planar might not always be non-planar, because sometimes you can redraw them as planar, and you'll see that in my first example. And that is why we are so grateful for Leonhard Euler and his contribution to mathematics. He was actually a Swiss mathematician slash physicist, engineer, astronomer, everythinger, who lived in the early 18th century, and he wrote a famous paper solving the 7 bridges of Königsberg problem, which I'll talk about next video. And he's basically the daddy of graph theory, and he blessed us with this theorem that can be applied to all planar graphs. So it goes, the number of vertices plus the number of faces subtract the number of edges is equal to 2. Or the number of vertices plus the number of faces is going to be equal to the number of edges plus 2. So this is the example that I was talking about, where you may come across a graph that appears to be non-planar at first, but upon closer inspection and redrawing, you realize that it's actually planar. So let's read the question. Consider the graph below. Part A, if the graph is planar, how many faces would it have? So when you think about planar graphs, your brain should automatically go to one of the versions of Euler's formula. V plus F equals E plus 2 is the one that I like to use, and that's how I'm going to find out how many faces this planar graph would have. So there are 1, 2, 3, 4, 5 vertices in this graph, plus our unknown number of faces is equal to number of edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, plus 2. So that means that F is going to be equal to 7, and that answers our question. If this graph is planar, then it's going to have 7 faces. So part B of this question is where we're going to redraw this graph as planar. Now, my hot tip here is to leave the vertices where they are, and instead, I want you to visualize all of the intersecting edges as lacy bands, loose lacy bands that can be pulled out of the way, okay? So looking at this, I want you to focus on all of these edges here in the middle that are intersecting, and focus on which edges you would be able to pull out of the way so that they're no longer intersecting with the other edges. So when I look at this intersection, I'm thinking that I can pull this edge out of the way, so it kind of looks like that. And then over here, I've got these intersections, and I'm trying to decide the least number of edges that I need to move so that they are planar. And actually, I'm not going to be moving this edge around here. I'm actually going to move this edge out here, and then I can move this edge out there, and then there'll be no overlaps left. So let me show you what I mean. I'm going to start by drawing the vertices in roughly the same places. And then I'm going to draw the edges in that are not intersecting with any other edges, so they are not going to be affected. And what did I say? I was going to move this edge out. So I've got an edge from there to there. I'm going to leave this edge where it is. So now I have gotten rid of that intersection. And by moving this edge outside, I actually only need to move this one out there. Whoop. And still keep these two edges in here. And that is my redrawn planar graph. I'm just going to count up the number of faces because it should be 7. 1, 2, 3, 4, 5, 6, and lucky last, the outside face is 7. Okay, let's move on to example 2. A connected planar graph has 7 vertices. 3 vertices of degree 2, 2 vertices of degree 3, and 2 vertices of degree 6. Part A, how many edges does this graph have? Okay, so every single edge has 2 ends, which means that it's going to contribute a degree of 2 to the entire graph. Which means that if I calculate the total number of degrees of the graph and then divide it by 2, I'm going to find out the number of edges. So let's go ahead and do that. I've got 3 vertices of degree 2 plus 2 vertices of degree 3 plus 2 times 6, and I'm going to divide all of that by 2. So I've got 6 plus 6 plus 12 is 24, divided by 2 is 12 edges. Part B of the question now asks me to draw this graph and verify that it is planar. I'm going to start with the first half of that question. So to draw this graph, I'm going to start with 7 vertices. 1, 2, 3, 4, 5, 6, 7. It is a connected planar graph, so I need to make sure that I don't have any isolated vertices. And because every single vertex has a minimum degree of 2, I'm going to start by connecting all of the vertices around in a circle like this, because now every single vertex has a degree of 2 and the whole graph is connected. So I've got connected 7 vertices. Well, all the vertices are degree 2 right now, so I won't check that yet. I've got 2 vertices of degree 3, so I can easily add a edge that connects 2 vertices. That makes those 2 vertices have a degree of 3 now. And then 2 vertices of degree 6. So between another 2 vertices, I'm just going to add a whole bunch of edges. So I've got this vertex here that has a degree of 2. I need to increase the degree by 4. So I'm going to add 1, 2, 3, and 4 edges there. So now I've got, let Let me just do some notes here. That has a degree of 2, 2, 1, 2, 3, 4, 5, 6, 3, 2, 3, and 1, 2, 3, 4, 5, 6. There we go. 3 vertices of degree 2, 2 vertices of degree 3, and 2 vertices of degree 6. So I have my completed graph here on the left. And I can't forget about the second part of the question that asks me to verify that the graph is planar. Verification of a planar graph, Euler's formula straight away. So I've got V plus F equals E plus 2. Number of vertices is 7. Number of faces is 1, 2, 3, 4, 5, 6, 7. That's going to be equal to the number of edges, which I will count even though we calculated it from above. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so I know I haven't made a mistake there. 12 edges plus 2. So 7 plus 7 is 14. 12 plus 2 is 14. Because the left-hand side equals the right-hand side, the number of vertices, faces, and edges of this graph satisfy Euler's formula, and therefore we can verify that it is, in fact, planar. So when I write here, I'll just do a little tick and then go, therefore planar. You know, keep it simple. So this is the third and final example for today. And to answer this question, we are going to need to recall some of the things that we've previously learnt. So let's read the question. Classify the following graphs by using at least one of the following terms. Okay, key word here is at least. That means that we can use more than one of these terms to classify each graph. And the terms that we have to choose from are simple, complete, bipartite, planar, directed, and weighted. So I'm going to go through the list of terms and try to pick out as many as I can for each graph. So starting with the first graph, I can tell that it is simple because there aren't any multiple edges or loops. It is also complete. It's actually a K4, and that's because there are 4 vertices and every single vertex is connected to all the other vertices. So this graph is complete. Now, to check if it's bipartite, I can color in my vertices, and already I can tell it is not bipartite because I can't separate the vertices into 2 distinct groups. It is planar because I can redraw one of these edges around the outside so that they're no longer intersecting. So that is planar. And it's not directed and it's not weighted. Moving on to the second graph, I can tell that it's definitely not simple because I've got 2 sets of multiple edges and a loop. It's not a complete graph because not every single vertex is connected to every other vertex. It's not a bipartite graph because, first of all, it's not a simple graph, and bipartite graphs fall under the umbrella of simple graphs. And I won't be able to separate the vertices into 2 distinct groups where the vertices aren't adjacent to each other. The graph is planar without having to redraw. And it's directed, we can tell because there's a few directed edges or arcs here, here, and here. And it is weighted, that's an obvious one. You can see that each of the edges are assigned a value. Now, moving on to my third graph, It is simple because there aren't any multiple edges or loops. It is not complete. It is bipartite, and that's obvious to see when the graph is nicely set out like this. I can see that the vertices can be divided into two distinct groups, and that within each group, the vertices are not adjacent to each other. So every single edge starts at a vertex in one group and ends at a vertex in the other group. Now, the graph is not planar. So a hot tip here is that if your graph contains a K5 or a K3, as it does in here, so there's a complete bipartite graph with 3 vertices in each set. That is a subgraph of this one here. And any graph that contains a K5 or a K3 is never going to be planar, okay? Take my word for that. Go and Google it if you want. So it is not planar, it's not directed, and it's not weighted. And that's it. Now, before we finish the lesson, I do want to point your attention to where else Euler's formula can be applied. And it actually works for all polyhedra. Now, a polyhedron is just a 3D solid that contains flat polygonal faces, straight edges, and vertices. Notice the similarity in the language used there? It's not a coincidence. So looking at this graphic here, you can start to tell why Euler's formula works for these polyhedra. And that's because you can unfold all of these polyhedra out to create these net diagrams. And what you'll notice about these net diagrams is that they are embedded in a single plane, aka drawn in 2D in a way where the edges are not overlapping with each other. So Euler's formula can be applied to every single polyhedron. Now, beyond planar graphs and solids, Euler's formula and graph theory can be applied in the tech world, especially for things like finding the optimal solution of the wiring of a computer chip, or to model the neural networks of AI. And at this point in humanity, who knows what else it might be applied to? It just acts as a springboard for us to mathematically think about shape and space in this universe. And that is just beautiful. And that is all I have for you today for planar graphs and Euler's formula. If you found this video helpful, please give it a like. And if you made it to the end of this video, you should probably subscribe and help my channel grow. Anyway, I'll see you in the next one. Bye.